Hello YouTube, I'm Fabio Mandrile, a PhD student at the Energy Department of the Politecnico di Torino, and today I will introduce you to my PhD research topic about simplified virtual synchronous compensators for grid services and grid support. First, something about me. I'm a last year PhD student in Electrical, Electronics and Communications Engineering. Before that, I got a master's degree in Electrical Engineering at the Politecnico. During my studies, I spent in total 1.5 years in exchange abroad, and I consider my PhD achievements the 12 publications I co-authored, the 2 industrial awards I won, the 3 power converter prototypes I realized, and the 7 master theses I co-supervised. My PhD research topic is about integrating renewable energy sources into the grid. In fact, in the past, the power system relied on synchronous alternators only, which were producing electricity from non-renewable sources such as coal. They were programmable, they were providing mechanical inertia thanks to the mechanical rotor, and they were generating a sinusoidal voltage due to their electromechanical construction. Tomorrow, we will shift towards converter-based production, such as from the sun or from the wind, which is, on the other hand, not programmable depending on the weather. It doesn't have mechanical inertia because, for example, solar panels don't have moving parts. And since it's based on inverters, it features switching harmonics. Therefore, there may be power system stability issues with large share of renewables integrated into the grid. So the question is how to provide grid ancillary services to guarantee such stability using static converters. Here comes the idea of making an inverter emulating a synchronous generator. First, we take a grid-connected converters and we transform it into a virtual synchronous generator by control means. The goal is to provide ancillary services to the grid, so inertial behavior to support the frequency, reactive support to support the voltage, harmonic compensation, and large short-circuit current injection. Therefore, we proposed the so-called Simplified Virtual Synchronous Compensator, or SVSC. Let's have a look inside the SVSC. We have a current control converter interfaced to the grid. Its references come from the SVSC model. This model is divided in several blocks. First, the mechanical part, which implements a simplified swing equation. Then, the excitation control, which is in charge of the reactive power channel. Finally, the virtual windings implemented on the DQ axis, which interface the excitation control and provide electromechanical damping. These windings operate as a virtual impedance, therefore generating the harmonic compensation references. And now let's see the SVSC in action. First of all, the inertial effect. We applied a frequency drop with a grid emulator, and the SVSC is injecting active power to support the grid frequency. Then we emulated voltage dips. For example, this 10% voltage dip, as you can see from the positive voltage envelopes. And the SVSC injects short-circuit currents with a decaying time constant, which depends on the parameters of the excitation control. Of course, the current has to be limited to comply to the inverter ratings, which are very different from the overload capabilities of synchronous machines. Finally, we prove the harmonic compensation capabilities by injecting a fifth harmonic distortion. As soon as the SVSC is turned on, this distortion is compensated and the voltage shape improves a lot. Drawing some conclusions, we have seen that a high penetration of renewable energy sources will affect the grid stability. Therefore, future grid-tied converters will be required to provide ancillary services, such as virtual inertia. The proposed SVSC can improve the behavior of such converters. My PhD contributions include the SVSC model operating as an add-on to enhance the behavior of grid-tied converters, and simplified converter models to further study the stability and interaction of multiple virtual generators at system level. That would be all from my side. Thank you for your attention.